Hi, in this video we're going to go over the division algorithm and hopefully get an understanding for what it is, and then we're going to do a proof. So the division algorithm says that given any two integers a and b with a greater than 0, then there exists unique integers q and r such that b can be written as some multiple of a plus a remainder r, and r is greater than or equal to 0 and less than a. So let's look at an example. So in this example we're going to let b equal 49 and a equal 9. And the division algorithm says that we should be able to write 49 as a multiple of 9 plus a remainder r, where r is greater than or equal to 0 and less than 9. So first what I'm going to do is set up a number line of all the multiples of 9. So here's our number line of multiples of 9, and we can see that somewhere in here we're going to have the number 49. So we can say that 49 equals a multiple of 9 plus a remainder r. Now we just need to find the remainder, so we can see that the gap between 45 and 49, that would represent the remainder, and in this case the remainder is 4. So we would write 49 equals 5 times 9 plus 4, and we can clearly see that 4 is greater than or equal to 0 and less than 9. So we've seen a pretty basic example of the division algorithm, and the concept I don't think is too hard to grasp. But the proof of this is maybe a little bit more difficult to see. So I want to do something that's going to help us with the proof later. We're going to write a set S, and this is going to be the set of all integers of the form b minus qa, where b minus qa is greater than or equal to 0, and q is representing an integer. So in terms of our example, our set S would look something like this. So the 4 here would be 49 minus 45, then we would get 49 minus 36, minus 27, minus 18, minus 9, minus 0, and then this one would be 49 minus negative 9, and it would just keep going on and on this way. So this is really just the set of all possible positive remainders we would get when we subtract b minus any multiple of a. And we wrote the set this way because now it's clear to see that the least element in this set, which is 4, this is the remainder that satisfies the division algorithm. Let's go ahead and start the proof of this. First thing to notice is that the division algorithm says that there exists unique integers q and r. So there's actually going to be two parts to our proof, existence and uniqueness. Let's start with existence first. We're going to start by writing the set S, which is going to be all the positive integers of the form b minus xa, where x is an integer. And the idea here is to show that the smallest element of this set will represent the remainder that satisfies the division algorithm. And in order to do this, we're going to use something called the well-ordering principle, which says that every non-empty set of positive integers contains a least element. So if we can show that our set S is non-empty, the well-ordering principle states that it contains a least element, which later we'll be able to show is our remainder. So in order to show that this set is non-empty, what we need to do is find an integer x where b minus x times a is greater than or equal to 0. And let's split this up into cases. The first case we're going to have is that b is greater than or equal to 0. So if b is greater than or equal to 0, we want to find an x where b minus x times a is in our set S. Well, let's see. If we just have x equals 0, then we would get b minus xa equals b minus 0. And since b is already greater than or equal to 0, this implies that b is an element in our set. So we have successfully found an x where b minus xa is in our set. So let's move on to our second case, and that would be b is less than 0. So in this case, you might want to play around with it a little bit and try to see if you can find an x on your own. But I'm just going to try letting x equal b. So if x equals b, we get b minus b times a, which of course can be simplified to b times 1 minus a. And we're trying to show that this is an element in our set. So at this point, let's look at a, and we know that a is greater than 0. That was from our definition up here. So we can see that if a equals 1, well then this whole thing is 0. And if a is greater than 1, 1 minus a is negative, but b is also negative, so this whole thing would be positive. So this just says that b times 1 minus a is always greater than or equal to 0. And so this just tells us that when x is b, b minus b times a is an element in our set S. So we've been able to find an element in our set S for both cases, proving that our set is non-empty. So by the well-ordering principle, our set has a least element. And let's let that least element be represented by r. So we're going to say let R be the least element in the set. Now we can conclude two things. First is that there exists an integer q such that R can be written as b minus q times a, and that's because it's in our set S, so it has to be of the form b minus xa. Second, we can note that R has to be greater than or equal to 0 since it's in our set S, and S is only positive integers. So we've shown that there exists an R greater than or equal to 0, and we've also shown that there exists a Q where we can write b equals q times a plus R. The last thing we want to show is that R is less than a. And in order to do that, we're going to use contradiction. So let's assume that R is greater than or equal to a. Well, since we know that R equals b minus qa, this tells us that b minus qa is greater than or equal to a. Now we can subtract the a from the right side, and we get that b minus qa minus a is greater than or equal to 0. And we can rewrite this, and we get b minus a times q plus 1 is greater than or equal to 0. But now we notice that this is of the form b minus x times a, and it's also greater than or equal to 0, meaning that it's an element of our set S. But b minus a times q plus 1 is always less than b minus a times q, which equals R, so this contradicts the fact that R was the least element in our set. So by contradiction, we have shown that R is in fact less than A, and this sums up the existence part of our proof. Let's move on to the uniqueness part of the proof. So when you're showing uniqueness, what you're really showing is that there is only one Q and one R, where we can write B equals QA plus R, with R greater than or equal to 0 and less than A. So in order to show that there exists only one Q and one R that satisfy this, we're going to actually assume that there are two different Q's and two different R's that satisfy it, and then show a contradiction somewhere along the way. So let's suppose that B equals QA plus R, and B also equals Q prime A plus R prime, where we have that R is greater than or equal to 0 and less than A, and R prime is greater than or equal to 0 and less than A. We want to show that Q must equal Q prime, and R must equal R prime, therefore proving that there is only one representation of this. So let's rewrite this a little bit. We get that R equals B minus QA, and R prime equals B minus Q prime A. Now subtracting R from R prime, if we rearrange and simplify it a little bit, we get that this equals A times Q minus Q prime. Now I'm going to change up these inequalities here just a little bit to make it easier to see. I'm going to multiply this first one here by a negative sign, and we'll get that negative R is greater than negative A and less than or equal to 0. And the second one will remain the same, so we'll have R prime is greater than or equal to 0 and less than A. Now if we add these together, we can see that R prime minus R is in between negative A and positive A, and this is just the same thing as saying that the absolute value of R prime minus R is less than A. So let's rewrite what we know over here. We know that R prime minus R equals A times Q minus Q prime. We also know that the absolute value of R prime minus R is less than A. So now let's take the absolute value of R prime minus R on the left-hand side. Well, we get that this will equal the absolute value of A times the absolute value of Q minus Q prime. And since we know from here that the absolute value of R prime minus R is less than A, we can conclude that this part here is also less than A. Now also notice that since A is greater than 0, the absolute value of A is just going to equal A. So we can write that A times the absolute value of Q minus Q prime is less than A. Now if we divide an A on both sides, we get that the absolute value of Q minus Q prime is less than 1. And since we have an absolute value here, we know that this has to be greater than or equal to 0. So we can write that the absolute value of Q minus Q prime is greater than or equal to 0 and less than 1. So here we have to notice that Q and Q prime are both integers. So subtracting Q prime from Q will also give us an integer. And since 0 is the only integer greater than or equal to 0 and less than 1, this says that the absolute value of Q minus Q prime must equal 0. And this in turn says that Q equals Q prime. Now if we just go back to our definitions of R and R prime, given that Q and Q prime are the same, this says that R must also equal R prime. And this concludes the uniqueness part of our proof. By proving existence and uniqueness, we have now shown that the division algorithm is true. Well, that's all for this video, so good luck with everything.